All right, example 1. We're going to verify the divergence theorem for the vector field capital F, and we have the cylinder of radius 2, excuse me, and height 5. So, and we're also told that the base lies in the xy plane. So, we can go ahead and sketch this if we'd like to. That's fine. So let's just go ahead and say we've got, there's top of our cylinder, this comes down. So then here we have our top of our cylinder. And then here we've got x-axis and, of course, y-axis. So there's our cylinder. This has a, what did we say? It has a radius of 2. So mark those 2 and 2. And we've got a height of 5. So, 5. Okay. So, verify the divergence for this vector field and the cylinder of radius 2 and height 5. So let's clean up the above. So important note here is that S is a closed surface. So normally a cylinder isn't closed. Okay. In this case here, what we're going to do is I've always just added this in. I always forget to type this. So let's just go ahead and say, we're just going to say closed. We're just going to add that in, okay. So we've got a closed cylinder. And verify the divergence theorem. So that means we're going to do this in 2 ways. We're going to calculate the surface integral. Well, I guess we'll do the surface integral first, and then we'll do the triple integral. So let's do the surface integral. So for the surface integral, we have to actually parameterize 3 different surfaces. We have the actual, let's go ahead and label these. We have the top. So we have S T for top. Then we have SB for bottom. And then we have the SS for the sides. Or how about we do SL for the lateral, right? For the lateral portion. Okay? So we have to parameterize this. So for the top, we can parameterize this by R of UV. We can go ahead and, since there's definitely circular symmetry going on here, I think while we could parameterize this not using ideas of polar, like as in sine and cosine, it's definitely going to be in our best interest to do so. So let's go ahead and say that we have V cosine U, V sine U, and then our height will be 5. Okay, and this is for U comma V in the domain of 0 to 2 pi, Cartesian product with 0 to 2 for V, the radius. So then we have the bottom. We'll do that since that's very similar in how we choose to parameterize this. This will also be V cosine U, V sine U, but here the Z component is 0. Our domain here will actually be the same though. This is for U comma V in the interval 0 to 2 pi, Cartesian product with 0 to 2. The lateral portion of the cylinder, I guess I should call this R1, or let's call this RT RB and yeah. Yeah, whatever. RL. We're going to have some subscripts on subscripts here. So in this case, we're still going to go around the cylinder, cosine U, sine U. But instead of filling it up, we're just going to have V draw up the side. So we go to some point. This is the point, this point here would correspond to cosine U, sine U, comma, 0. But then we want to trace this entire line up. So here, this Z component will vary. So V will go from 0 to 5. And we'll imagine this just traces up. Then we move a little bit and we'll trace up. And we do this all over the cylinder. So for U comma V in the interval 0 to 2 pi, Cartesian product with 0 to 5. Okay. So now that we have that, that's a lot of work already. This is kind of crazy. We're going to run out of room probably. So let's go ahead and just move that over here and go back. So now that we have this, we can see that the double integral over the surface S. So here it's important to note that S, I'll write, S is the top glued with the bottom, glued with the lateral portion. So this f dot ds is equal to the surface integral of the top plus the surface integral over the bottom plus the surface integral over the lateral portion, f dot ds. Okay. Once we have that, we can go ahead and chip away at this a little bit. Note that since the domain for ST and SB are the same, we should be able to condense these two together in such a way. Oops. So we'll do that. So this would be the double integral over, I guess I'll call these, this will be, let's call this domain for top and bottom, because it's the same, so d sub tb, and this will just be d sub l. So then, this will be the double integral over d tb of our vector field f, but with appropriate replacement by these components. So this will be y, yz, and z squared, dotted with, we need our normal vector here. So our normal vector here I will write out and write underneath of it what exactly it is. So this will end up being, for the top, this will be 0, 0, v, and this is exactly RTU crossed RTV. Oops, excuse me, other way around. This should be RTV cross RTU in that order. So essentially the V partial of this crossed with the U partial of this. And then of course, that's going to be dA. Plus the double integral over d sub tp of, we'll have y, which is v sine u, yz, which is 0, and z squared, which is 0, dotted with, again, I'll write down in this format here, this is going to be 0, 0, negative v, which is r sub bu cross r sub bv. So it is the u partial of this crossed with the v partial of this, dA. Plus, will I have room? We're going to have the double integral over d sub L for the lateral domain D. This will be our replaced version. So this will be y, which is the sine of u, yz, which is v sine u, and z squared, which is v squared, dotted with the appropriate derivative, which again I will write down. This is going to be 2 cosine u, 2 sine u, oh yeah, that just reminds me here, sorry, from earlier, this is a circle of radius 2. Circle of radius 2. So this should be a 2 here in front of each of these. Well, in front of the first two at least. My apologies. So yeah, right here, a little correction. Should be 2's. Two cosine u, 2 sine u, 0. dA. Oh man. Okay, so that is fun. So we are going to take advantage of this space here. And I'm just going to continue up here. So continuing. So if we continue, I can effectively write this as just, I can pretty much just group these first two terms together because they're over the same domain. So that's nice. So we'll have the double integral over dTB. When we do our dot product here, we should just have 25v, that's nice, plus 0 dA. That's really nice. And let's just make this 25v. So this will be 25v dA plus the double integral over dl. We'll go ahead and do this. Dot product here. This will be 2 sine u cosine u plus 2v sine u. Yeah, that's it. Well, sine squared u, excuse me. Sine squared u. dA. Okay. And let's just double check everything. Looks good so far. All right. Oh, one thing really quickly here. I think for this one here, I should have a 2 here. Sorry, I didn't correct this 2. There should be a 2 there from earlier. Remember that this we modified this. Right, so this is our y, z, z squared. That's our vector field. So our y should be 2 sine u, our yz, this should be a 2v. Excuse me. Okay. That looks better. So up here, this would be 4. And then we'd also have, down here, we'd have 4v sine squared u. My apologies. That is looking better. Okay. Now that we have that, we can go ahead and, let's see here. 25, our domain, let's say dv du, so u is 0 to 2 pi for this one. V is 0 to 2, is it? Yep. So then this is v du, plus this is 0 to 2 pi, integral 0 to 5, and this is 4 sine u cosine u, plus 4v sine squared u. And what we can do here, remember with sine squared of u, this is equal to 1/2 1 minus cosine of 2u. So this can turn into 1/2 times 4 is 2, v times 1 minus the cosine of 2u. dv du. All right. So for this one here, we can definitely do a u substitution or a w substitution. This will work out. And notice that the bounds will end up being both 0. So that means this the u integral will just be 0. The v integral will be 5, but 0 times 5 is 0. Okay, so that's nice. You get in the habit of doing these integrals. So if we take a look at that, this will just be u minus 1/2 sine of 2u between 0 and 2 pi, which is going to end up being just 2 pi. Now the v portion of this integral, the 2v, this will just end up being v squared between 0 and 5, which is 25. So this entire thing turns into 25 times 2 pi, which is 50 pi. Similarly, this one here will turn into 1/2 v squared between 0 and 2, which is 4/2, which is 2. The u integral here will just turn into 2 pi. So this is going to completely, the full thing, turn into this whole integral turns into 25 times 2 is 50. 50 times 2 pi is 100 pi. So this would be 100 pi. So at the end of the day, this entire thing is 150 pi. Okay. So, with that out of the way, we can now tackle it. So let's make a little numbers here. So we start here, 1, move all the way down to the bottom, then we move up to here. Now we're going to move, where are we going to move? Let's just go up here. So we're going to do the triple integral. Okay. So for the triple integral, we need to know the divergence. So the divergence of the vector field F is the x partial of y, right? We haven't done divergence in a while. So it's the x partial of y plus the y partial of yz plus the z partial of z squared. Oops. Which is equal to 0 z 2z added together. So this is 3z. Okay. So the triple integral over w of the divergence of f dv is equal to the double integral over w 3z dv. So now what is our volume? Or so what is w? W is the actual solid cylinder. So it's not just the surface of the cylinder, it's everything within the cylinder. So it's important to note here that the boundary of W is our surface S. So this is the full thing. So we can actually describe W in terms of cylindrical coordinates. We could describe this W here, we can describe W as, well, we can say that Z is between 0 and 5. We can say that R is between 0 and 2. And we can say that, 0 and 2. And we can say that theta is between 0 and pi over, or sorry, just 2 pi. So then, this is cylindrical, so this would be, factor out the 3, this would be 3, we'd have 0 to 2 pi, 0 to 2, 0 to 5, z, and dv is r dz dr d theta, which is equal to, there's no r or theta in here, so we're definitely going to end up having 3 times 2 pi times 2. Oops. Not times 2. There is an r in there. There's no theta in there, excuse me. So we'll have 3 times 2 pi. But then we will have, for the r integral, we'll have a half r squared between 0 and 2. And we will have a half z squared between 0 and 5. Okay, so this will be 6 pi over 4 times 4, because, right, this turns into 4, this one. I factor out the 1/2 and the 1/2, there's the 1/4. 2 squared is 4, and 5 squared is 25. Well, 4's cancel. 25 times 6 is 100 plus 50, so 150 pi. This is a long example, But it does show you how nice actually integrating the triple integral can be, because having three surface parameterizations is a huge pain.